Now let's turn to insertion. This is where linked lists really shine. We will see how to add a node by changing just a couple of pointers with no shifting at all. Let's insert a new node at the front. On the left is the before picture. Head points at node 10. Node 10 points at node 20, and node 20 ends with null. This is our starting list. Now the after picture. We make a new node with value 5. First we point the new nodes next at the old first node. Then we redirect head to the new node. Nothing else moved. Just 2 pointer rights, and node 5 is now the head. This is the key idea. Order matters. Set the new nodes next to head before you move head. If you move head first, then head already points at the new node. So the right new node arrow next becomes head, makes the node point at itself, and the rest of the list is lost. Your turn again. Inserting 5 before the current head needs exactly 2 pointer rights. 1. X arrow next becomes head. 2. Head becomes X before the reveal. Predict for yourself. Does the order matter? What happens if you do head becomes X first and then X arrow next becomes head? This is the trap. You may think 2 separate rights can go in any order, but if you move head first, then head already names the new node. So X arrow next becomes head, makes the node point at itself. The rest of the list becomes unreachable. One reversed line silently loses every existing song. Now compare the cost. The array front insert had to move all 5 songs. Big O of n, this moves 0 existing nodes. Big O of 1. That gap is the whole reason linked lists exist. Now let's insert at the head, one change at a time. The old list head to 10 to 20 stays on screen the whole way. Step 1. Allocate. We run X becomes malloc and get a raw node. Its data and next fields are garbage for now, shown as question marks. Step 2. Write the data. We run X arrow data becomes 5. The new node now holds its value. It is still not linked to anything, so its next is still garbage. Step 3. Link. We run X arrow next becomes head. Node 5's next now points at the old first node. Watch carefully. Head itself has not moved yet. It still points at node 10. Step 4. Move head. We run head becomes X head now points at node 5. Done. Nothing moved, so this is big O of 1. And notice the order. We linked the new node first, then moved head last. Insert at head changes which node is first, so the caller's head must be updated. This is the way we use in this chapter. The function returns the new head. We malloc a new node called X. If malloc fails and X is null, we return the old head unchanged. Then we set X arrow data to K. We set X arrow next to head, so the new node points at the old first node. Then we return X. The caller writes head becomes insert head of head in K. Here is why we return the new head. Head is passed by value. Assigning to it inside the function changes only the local copy. Returning the new node is how the caller learns that the head moved. There is a second way. We take a node pointer to pointer called headref. This is the address of the caller's head, so we can write straight into it. Again we malloc X and return if it is null. We set X arrow data to K. We set X arrow next to star headref, the old first node. Then star headref becomes X. That line writes the caller's head for us, so no return value is needed. Now a learning check. A student writes head becomes X inside a function that takes head by value, calls it, then prints the list, and the 5 is missing. Why and what one change fixes it? Pause and think. Here is the answer. Because head is passed by value, that assignment changes only the local copy. The caller's head never moves, so the 5 is missing. The fix is one of these 2 patterns. Return the new head, or take a node pointer to pointer and call it with ampersand head, the address of head. Now let's add a node at the end. With only a head pointer, we must first walk all the way to the last node. The table on the left is that walk, 1 hop per row. It visits every node in turn, and the rows stay. Step 1. Cur is at 3000, node 10. We check its next field. It holds 7000, which is not null, so this is not the tail. We advance cur. Step 2. Cur is now at 7000, node 20. Its next holds 4000, again not null, so still not the tail. We advance once more. Step 3. Cur is now at 4000, node 30. Its next field is null, so this is the tail. The walk stops here. Now the append on the right. First we allocate. We malloc a new node holding 40. It is not linked in yet, so its next is null. Then we link. We set cur arrow next to X, so the old tail now points to the new node. The new node is appended. Here is the cost to watch. With only a head pointer, each tail append is big O of n because of the walk. Building a list this way, one append at a time, is big O of n squared. If we keep a separate tail pointer, each append becomes big O of 1. We do that in Chapter 5. This is insert end in C first. We malloc a new node called X. If X is null, malloc failed. So we return head unchanged. We set X arrow data to K. We set X arrow next to null, because the new node becomes the tail. If head is null, the list was empty, so X is now the whole list and we return it. In the empty list case, we return X directly, so the caller updates its head. If the list is not empty, we still need to walk to the last node. We do that next. Now the list is not empty and X is ready. We set cur to head. While cur arrow next is not null, we move cur to cur arrow next. When the loop stops, cur is the last node. We set cur arrow next to X, linking the old tail to the new node. Then we return head. The time is big O of n. The walk to the tail dominates. The link itself is big O of 1. Now suppose we already hold a pointer P to a node in the list and we want to add a new node right after it. Picture a train. Each car is coupled to the next one. To add a car in the middle, you uncouple one joint. You hook the new car to the car behind. Then you hook the car ahead to the new car. Just 2 couplings. The rest of the train never moves. That is insert after. We set X arrow next to P arrow next, then P arrow next to X. This is the before picture. The pointer P points at the node with value 20. That node points forward to node 30. We want to slip a new node in between them. This is the after picture. The new node 25 sits between them. Node 20 now points at it and it points on to node 30. Only 2 joints changed. Nothing else in the list moved. The order matters. First copy P arrow next into X arrow next, then overwrite P arrow next. If you do it the other way, P arrow next already equals X, so X arrow next becomes P arrow next points the new node at itself, and the successor 30 is lost. Your turn. We want to splice 25 after P, the node with value 20. To do that, we overwrite P arrow next. But right now P arrow next holds the address of node 30. That is the successor we must not lose. These are the 2 lines. Line A is X arrow next becomes P arrow next. The new node copies P's old successor. Line B is P arrow next becomes X. Now P points at the new node. Predict, before the reveal, which line has to run first and why. Think about it. You may want to run line B first. P arrow next becomes X. But then P arrow next already equals X, so line A, X arrow next becomes P arrow next, sets X arrow next to X itself. Node 30 is orphaned. Save the old link with line first. Before you overwrite it with line B, try to answer it yourself before the next slide. Let's splice a node and after P, one change at a time. The chain P to 20 to 30 stays on screen the whole way. Step 1, allocate. We malloc a raw node. Its data and next are garbage for now. Step 2, write the data. We set X arrow data to 25. The node now holds its value. It is still not linked from either side. Step 3, and this order matters. We run X arrow next becomes P arrow next. So node 25's next copies the address of node 30. We save the old successor first. Notice P still points at node 20. Step 4. Now we run P arrow next becomes X node 20's next now points at the new node. The new node is spliced in. We saved the link in step 3 before we overwrote it in step 4. Just 2 writes, so this is big O of 1. This is insert after. In C first we check P if P is null. There is nothing to insert after, so we return. Then we malloc a new node called X and return if it is null. We set X arrow data to K. Now the 2 writes in a fixed order. First, X arrow next becomes P arrow next, so the new node inherits P's successor. Second, P arrow next becomes X, so P now points at the new node. The time is big O of 1 if you already hold P. The 2 pointer writes are cheap and there is no walk. But finding P by value in the first place is a separate search, and that is big O of N.